In this presentation, we will explore what KVP is and how KVP can be used to manipulate radiographic technique. If you're not familiar with how X-rays are produced, you might want to consult my How X-rays are Produced or my Bremsstrahlung videos for more information. Also, I reveal some facts about KVP you might find surprising. The term KVP stands for kilovoltage peak. Voltage controls the energy applied across the X-ray tube during an exposure. This determines the energy imparted to the high-speed electrons that move from the cathode to the anode. When the electrons are decelerated by the target of the anode, their energy is converted to X-ray photons and heat. KVP controls the energy of the electrons and affects the penetrating power of the X-ray beam. The K in kilovoltage is short for 1000, so any number of kilovolts can be multiplied by 1000 to derive the true number of volts in use. Most X-ray techniques fall in the range of 40 to 130 kilovolts. In terms of volts, this translates from 40,000 to 130,000 volts. The P in the term KVP stands for peak energy. Whenever we select a kilovoltage, we are selecting the peak energy our X-ray photons may achieve. Just because we send a high-speed electron across the tube with 70,000 volts of energy doesn't guarantee the X-ray it produces will contain that 70 kilovolts of energy. More about this later. On the surface, how KVP works is fairly simple. The higher the KVP, the more likely an X-ray photon will penetrate the patient's tissues and interact with the image receptor. The first X-ray beam represents a high-energy beam. Most of the X-ray photons penetrate the absorbing material and reach the image receptor below. This would represent a high-quality beam that does not contribute much to patient dose, but has a lot to do with image formation. Whereas the low-energy beam, shown below, is mostly absorbed in the block above the imaging plate. This represents a low-quality beam that contributes more to patient dose and little to image formation. Aside from KVP, what affects the penetration of an X-ray beam? Number one on the list is part thickness. The thicker a patient is, the less radiation penetrating the part. To compensate for a loss of radiation reaching the image receptor, the radiographer will need to increase the amount of radiation used for the exposure or increase the penetrating ability of the X-ray beam. Thinner parts are less likely to interact with the X-ray beam, therefore more easily penetrated. This results in the need for KV to be reduced in order to prevent overexposure. The density of a part also affects the amount of radiation penetrating a patient. Most of the densities in our body can be attributed to the amount of calcium present in a given tissue or organ. The more muscular the patient is, the less radiation penetrating the patient's body. Muscle is denser than fat. Muscles contain more calcium than does fat, so adjustment of the technique may be necessary for knees to pelvis and elbow to shoulder exams for heavily muscled individuals. Hollow organs, body cavities, alimentary canal, or blood vessels can have contrast media introduced to make them denser than surrounding tissues by the introduction of iodine or barium-based compounds. This reduces the penetration of the radiation. On the other hand, air or gas can be introduced or trapped in alimentary canal or body cavities, allowing more beam penetration. This explains why a reduction of radiation amount or penetration is recommended when imaging possible emphysema patients. Let us now explore the definition of KVP. Just what does peak at the end of KV acronym mean? Here we have an example of a control panel with two KV selector dials, a major and a minor setting. The major dial sets kV in increments of 10 and the minor in increments of 1. I'll set the major selector to 70 and the minor selector to 4 for a peak kV setting of 74 kVp. Below the control panel is my patented KVP-ometer. The KVP-ometer displays the energy of the output of the X-ray tube. Note that when I make the exposure, the tube does not provide a single X-ray energy, but a spectrum of energies ranging from 0 kV to the peak of 74. Also note that the bar is darker in the middle, indicating less of the low energy and high energy photons were produced. This means that when we select KVP for a particular examination, we produce a range or spectrum of X-ray energies, and the energy selected is not representative of the most prominent X-ray energy produced. This slide depicts the energy distribution curve for a selected KVP. The x-axis records the various energies produced by the tube, and the y-axis plots the number of X-ray photons produced at that energy level. Note that the curve has a bell-shaped appearance. This shape is a result of Bremsstrahlung interactions in the target combined with the likelihood of low-energy photons being absorbed by beam filters. For a more detailed explanation of this curve, see my presentation on Bremsstrahlung radiation. Note that the peak energy selected for this exposure was indeed 74 kV, and there are few photons produced at this energy level. Let us draw a line at about 24 kV. I've selected this level somewhat arbitrarily because it is dependent on the thickness and density of the part under examination. It would move higher for thicker or more dense tissues and lower for thinner or less dense tissues. Photons below this level contribute mostly to patient dose due to their low energy level. X-ray tubes may employ added filtration to minimize these photons from exiting the tube and contributing to patient dose. Photons above this energy increasingly contribute to image formation as the energy increases. So the P in KVP stands for the peak energy employed for a given exposure. Due to the way X-rays are produced, X-rays are a mixture of energies. Heterogenic refers to the fact that all X-ray beams are comprised of many or a range of energies, whereas a homoenergetic beam is a beam comprised of few or just one energy. For every X-ray technique we select, the beam is a spectrum of energies. At 74 kVp, the X-rays that range from 0 to 74 are produced. So the selected KVP is the peak energy a given exposure will have. To protect the patient and keep radiation dose low, you will hear that high kV, low MAS techniques achieve this goal. High kV techniques do indeed represent less patient dose, since more radiation penetrates the patient tissues and less radiation is absorbed by those tissues. More penetration means more radiation reaching the image receptor. Items that were displayed as white are now displayed as shades of gray. In film screen days, this would cause a loss of contrast, but in the digital era, contrast is controlled by the computer's construction algorithms. If a loss of contrast is no longer a consideration, then why not use high kV, low MAS exposures for all exams? The computer uses density differences to delineate objects that absorb radiation at a similar rate. High kV exposures even out these differences and make discrimination for the computer a harder job. Bottom line, high kV, low MAS techniques reduce contrast resolution or visibility of detail. This is why mammography uses low kV in a range of 26 to 30 kV to image breast tissue. Glandular tissue, breast fat, and breast masses are similar in density and can be small in size. So high MAS, low kV techniques maximize the chance of the computer visualizing the pathology. Some facts regarding KVP are: altering the KVP level changes the penetrating power of the X-ray beam. I've seen quite a few presentations get this particular fact wrong or are unclear regarding radiation amount. The KVP does not change the amount of radiation produced by the X-ray tube. MAS and MAS alone controls the amount of radiation production for a given exposure. A change in KVP will alter the amount of radiation exiting the tube. An increase in KVP will increase the penetrating power of the X-ray photons, and the more photons will penetrate the tube wall and filters. In addition to more radiation exiting the tube and collimator, more radiation will penetrate the patient and contribute to image formation. In the radiography, the 15% rule still works. Because of image correction by the computer, the 15% rule does not make the image darker or lighter. 15% changes will cause a LGM value to increase or decrease by 0.3, which is equal to 2 times change in non-logarithmic terms, or will cause the S number to decrease or increase by a factor of 2 times in the case of systems using S values for exposure evaluation. To cause a 2 times increase in exposure, add 15% to the KVP. A 15% increase in KVP will cause the LGM to increase by 0.3 or the S number to decrease by 1/2. To have the opposite effect, subtract 15% from the KV to decrease the exposure to the imaging plate by a factor of 2 times. A 15% decrease in KVP will cause the LGM to decrease by 0.3 or the S number to increase by a factor of 2 times. Thank you for your kind attention. This ends my presentation on KVP basics.